Hi. All right, so let's take a look at the impulse worksheet. All right, so in the impulse worksheet, we're using the fact that impulse, by definition, is the force times the change in time. And remember, we got this thing from Newton's second law of motion. I'm just going to put this up here. Newton's second law of motion stated that force was equal to mass times the acceleration. Well, remember, the acceleration, I'm going to rewrite this, is equal to, so we take the mass, the acceleration is the change in velocity over the change in time. And so if we rewrite this whole thing, you get this quad formula that the force times the change in time is equal to mass times the change in velocity. Now, as we discussed before, this mass times change in velocity, that's defined as the change in momentum. This other side, so this side we've already discussed, this other side is going to be what's called impulse. And so we get kind of a quad formula here. The J is equal to F delta T, which is equal to M delta V, which is equal to delta P. In your reference table, you won't find this, and I encourage you write this in. But what you'll see, or what I encourage you to write in, is that J, or in your reference table, you'll see F delta T is equal to delta P. And they leave off the M delta V part. And that's because right above it, they tell you that P is equal to M times V. So this is in your reference table, but I encourage you, write this next to it. Write this next to your J F delta T equals delta P. That way you have it and you're used to it and stuff like that. So going back to our worksheet, we have a football player kicking a ball with a force of 50 newtons. Find the impulse of the ball as the foot stays in contact with the football for 0.01 seconds. So again, let's do as we always do. Let's guess this. So we know we have a force of equal to 50 newtons. We have a time of 0.01 seconds, and we're looking for the impulse. So we're looking for J. So J is equal to F delta T, the change in time. So we're going to take the 50 newtons, and we're going to multiply that by the 0.01 seconds. And of course, then when we do that, we're going to get 0.5 Newton seconds. Now, real quick, just a quick discussion on this. Remember, we said the momentum, the units for momentum were kilogram meters per second. We're saying their units for impulse are newtons times seconds. And these are actually the exact same units because a newton is a kilogram meter per second squared. So if you multiply that, you're just going to get a drop on the squared and you'll get kilogram meters per second. So they can be used interchangeably. Traditionally, impulse is measured in Newton seconds, and traditionally momentum is kilogram meter per second, but they are the same thing. All right, so let's look at B. A hockey player applies an average force of 80 newtons. So let's guess this. So a force of 80 newtons to a mass of 0.25 kilograms for a time of 0.2 seconds. Determine the impulse. Well, J is equal to F times delta T, force times time, so we don't need the mass for this particular one. We're going to take the 80 newtons, and we're going to multiply that by the 0.2 seconds, and we're going to end up getting 16 Newton seconds. So again, we talked about this before. Remember that oftentimes they'll give you more information than what you need. You have to put down what you have, what you're looking for, and then go find the equation that'll let you solve for that. And you don't necessarily have to use all of the information that they give you. All right, so part C, Aunt Mary needs to hang a picture in her bedroom. She uses a hammer to drive a nail into the wall. Find the force. So we're looking for F. So F is question mark here. And we have a time of 0.5 seconds, so 0.5 seconds. And we're given the impulse of 25 Newton seconds. Now you'll notice in there they do no decimal, no multiplication point in there. I always put the multiplication point in there. It really doesn't matter. It's whatever your preference is. I always put it in. That's just my personal preference. So let's go back, and we've got J is equal to F times delta T here. So we've got 25 Newton seconds is equal to the force applied, and then times the time of 0.5 seconds. And so when we do this, we find we have a force of 50 newtons. Okay, so if we look at exercise 2 here, we have a mass of 0.5 kilograms, and we have a force of equal to 10 newtons, and we have a time of 0.1 seconds. What's the change in the velocity of the basketball? Now, this is a perfect time for us to use that J is equal to F delta T, which is equal to M delta V, which is equal to delta P. And the reason for that, we're looking for the change of velocity, so we're looking for delta V, and we're given the force. So if I replay this in, I've got 10 newtons times my 0.1 seconds, and that's going to be equal to my mass of 0.5 kilograms, and then that'll let me solve for delta V. So that way I can use just this section of my equation to solve for what I need. And so when I solve for that, I find that I'm going to get a change of velocity of 2 meters per second. All right, and finally, on this one, part B, the space shuttle burns a fuel rate of 13,000 kilograms each second. Find the force exerted. Okay, so I'll put this down here, force question mark, that's what I want, in 2 seconds. So we have time of 2 seconds. And we know the change of momentum, so delta P is equal to 325,000 kilogram meters per second. Okay, so now you're looking, okay, well, what's this 13,000 kilograms per second? In reality, this is, if you just look at the units, this is the mass per unit time. Now, this isn't necessarily anything we need right here, because I know that delta P is equal to mass times the change of velocity. You're like, well, that doesn't help me because I'm looking for force. But remember, it's also equal to the force times time, and that's equal to J. So in this instance, I'm only using delta P and force times time. So I know what that is. My change of momentum is 325,000 kilogram meters per second. And I'm looking for my force, and I know that my time is a whopping 2 seconds. So I didn't need that mass per time that I had before. So when I solve for this, I find that I get a force of 162,500 newtons. So a lot of force there. Okay, and finally we're going to look at exercise 3. Okay, and it gives us a lot of stuff here. So let's put this off to the side. It says a van of mass 1,200 kilograms. So mass is equal to 1,200 kilograms. Okay, it's moving at a velocity of 8 meters per second. So we have a velocity of 8 meters per second when it's involved in a head-on collision with a lorry moving in the opposite direction. Assuming the van comes to a stop. Okay, so we had an initial velocity of 8, and now it comes to a stop. So I got to put in here that we have initial velocity of 8 and a final velocity of 0 meters per second. So that's everything I now know. So they want me to calculate the momentum of the van before the collision. So I'll put that down here. So this is kind of like P initial, because it's the mass times the initial velocity. So in this case, it's going to be 12,000 kilograms, or sorry, 1,200. I put that in the wrong spot. 1,200 kilograms. I'm going to multiply that by my initial velocity of 8 meters per second. And when I do that, I'm going to get 9,600 kilogram meters per second. They want us to work out the momentum of the van after the collision. Well, that part's easy, because now we're looking for P final, so that's mass times V final. So we still have our 1,200 kilograms, but now our velocity is 0 meters per second. So that's going to be nice and easy, 0 kilogram meters per second. So now they want us to find the change in momentum of the van. Now remember, change in anything. Change in anything, so in this case, change in momentum is the final momentum minus the initial momentum. So my change in momentum is 0 kilogram meters per second minus that 9,600 kilogram meters per second. So what's happening here, we actually have a change in momentum of negative 9,600 kilogram meters per second, which makes sense. That's how much momentum that it's losing. All right, and then finally, part 4, if the van took 0.3 seconds to stop, calculate the force. So we're given another given here. We have a time of 0.3 seconds, and so we need to find the force. Okay, so initially, I don't know what the force is, I don't know the acceleration, the mass. So what I can do here is I can say, well, wait, I do remember that the change in momentum is equal to the mass times the change in velocity. Yep, but it's also equal to the force times the change in time, which is equal to the impulse. And so once again, I'm going to use my change in momentum and my force times the change in time to solve this particular problem. So I'm going to take my change in momentum, a negative 9,600 kilogram meters per second is equal to the force applied times the time, which is 0.3 seconds. And so the force exerted is going to be a negative 32 1,000 newtons. So lots of force there. These drivers are probably not in good shape after this collision. And it's negative because it's causing them to stop. It's causing them to decelerate, to slow down. The acceleration is the opposite direction of their motion. So I hope that helped. And if you have any questions, again, stop on in. Everybody have a great day. We'll see you later. Bye.